Hello, it's week 6, and let's take a look at this week's lab journal. I'm downloading it. All right, so there's the usual table to fill out, and you've been getting pretty good at that, so I don't think I need to say anything about that. So we have here um, a pool table, and one thing I want to say, there are some issues actually with this problem set that need to be corrected. So first of all, you can see from here that there's 4 divisions per major division. 4 into 50 is 12 and a half. It says here 10 centimeters. So it really should be 12 and a half. So then it asks, what are the coordinates of the Q disk? Well, the Q disk is the white one right here, and you can read those off by yourself, right? It's minus 100, 0. What are the coordinates of the 8 disk? That's the black one here. Well, you can just read it off. It's 150. So this part is pretty simple. The white star marker. You have to think a little bit on this one. So it's, somewhere between 150 and 200. If each one of these markers is 12 and a half, then just go 1, 2, 3 times 12 and a half and add that to 150. That's the x coordinate, right? And then uh, there's 50 right there, and then there's 1, 2, 3 above that. 3 times 12 and a half plus 50 is the y coordinate. Okay, so that's the answer to that one. What are the x and y components of the displacement vector that points from the center of the 8 disk to the center of the white star marker? All right, so we want a vector that goes from here to here, so I'll draw it on the form here. Vector goes like this. So all we have to do is define it by the displacement from the 8 disk to the white star marker. All right, so all we have to do is count the number of squares, multiply that by 12 and a half to get the x component, and then the number of vertical squares times 12 and a half to get the y component. So I have, let's see, 4 there, 5, 6, 7 times 12 and a half, right? So 7 times 12 and a half. It's 87.5. So the x coordinate or the x component is 87.5. Hope you can write more neatly than I can here, or type it in, right? And the y component, go up here. 1, 2, 3. 3 times 12 and a half. Where'd my calculator go? There it is. 3 is 12.5. 37.5. Okay, pretty easy. All right, the player is only permitted to move the cue disk vertically to set up the shot. What location is needed so that if you fire the cue disk directly at the 8 disk will go directly through the white star marker. So you want it along this line. Now I can't draw a perfectly straight line here. Okay, but it looks like we have to go negative. To make these objects line up, this slope has to be the same as the slope between the 8 disk and the star here. So the displacement in the vertical direction is the coordinate 50 minus the coordinate of the new position of the Q disk. So it's 50 minus y. We want to find y. And then the horizontal displacement is the coordinate of the 8 disk, which is 100, minus the coordinate of the Q disk, which is negative 100. And that has to equal the rise over the run of this segment here. And you can just count the boxes. We're just measuring slope. We don't have to have the actual units. So it's 3 boxes high and 7 boxes wide, right, across. So that's 7. So now we set up the equation. So we have 50 minus y, 50 minus y, that's the rise, over the run, 100 minus negative 100. Well, we know what that is, right? It's 50 minus y over 200 equals the slope of this segment here, right? Right here, which is 3 over 7, rise over run, 3/7, same slope. So if you solve for y, that'll give you the answer. Okay. Moving on to 4, it asks, okay, from this new location, you shoot the disk towards the 8 disk and then answer the following question. So at what angle from the horizontal will the Q disk move? So we're trying to find this angle, which, we've solved this so that it's the same angle as this angle. We'll call it theta. So the tangent of theta is 3/7. The tangent of theta is 3 over 7, right? It's 3 boxes up, 7 horizontal. That means that the angle is the inverse tangent of 3/7. Okay, so B, it asks, what is the magnitude of the impulse that you must apply to the disk for it to have a speed of 1 meter per second? Well, the impulse is just the change of momentum. So we write the impulse is the change of momentum, which is the final momentum minus the initial momentum. Well, if the puck or the disk has a mass of 160 grams, that's 0.16 kilograms, times the velocity. Okay, this is the final momentum, which is 1 meter per second. Minus the initial momentum, it started from rest, so it's 0, right? So you can work out the arithmetic there. Assuming the tip of the cue stick only contacts the disk for a millisecond, thousandth of a second, what's the average force? Well, the force is just the rate of change of momentum, or the impulse divided by the time. Okay, you have delta t. This is delta t right here. And you know what delta p is from this simple expression, right? What are the components of the Q disk's momentum vector after being struck by the Q disk? Well, you have the momentum, which is just this value. It's just P final, right? Because P initial is 0. So what are the components? Well, the X component is going to be the momentum, final momentum, times the cosine of the angle, right? Because the momentum vector is in this direction, in the direction that you're hitting the disk, right? So you have this angle, this component this could represent the momentum. So you multiply the hypotenuse by the cosine to get the x component, and you multiply the hypotenuse by the sine to get the y component. Yeah. So that's the x component, and the y component is given by this. And you already know what theta is from this expression. What's the kinetic energy of the Q disk after it's struck? Well, kinetic energy is just 1/2 the mass of the disk, 0.16, right? You have to put it in kilograms times the velocity squared, 1. Pretty easy. All right, 5, it's not a great question, really, but it can be answered. So, what angle is measured from positive x-axis is the lower fragment following. So what happens is you fire the Q disk at the 8 disk, and the Q disk stops, and the 8 disk continues. And then the 8 disk fragments into 2 parts, and the upper fragment, having a mass of 100 grams, stays along that path. And it's moving at 1 meter per second, the same speed as what the 8 disk had initially. So this becomes a trivial answer. This is trivial. Right? I mean, to conserve momentum, you could say, the momentum, the initial momentum has to be the final momentum. So we know what the initial momentum was, and we know the components, right, from here. So you would write this px equals the total x momentum after the disk splits up. So the disk splits up, so it's going to be going, has a mass of 0.1 kilograms times the velocity, which was 1. Times the cosine of the angle. And then you have the other portion, right, which is the remainder, which has to be 0.06 times whatever the velocity is, times the, this is the x component, so it's the cosine of theta 2, right? So we have these two fragments. One is going at theta, and the other one is going at theta 2. And then the y component, py, equals, again, 0.1 times 1 meter per second times sine of theta. That's the theta you found. It's this theta here, same theta, that one right there. Plus the other portion, which is going 0.06 times whatever its velocity was, whatever its v is, times the sine of the angle. Okay, so we have two equations and two unknowns, and you can solve that. Okay, so I'll leave that to you. You'll find, you can find the angle from this, and then you find v here. Okay, solve for v. And really, you don't, if you think about it, just common sense will tell you what the angle in v is, because if one portion is moving that direction, which direction does the other portion have to be going to conserve momentum? You really don't need to do this calculation. Hint, hint. Okay, and then is the kinetic energy conserved in the collision? So now you have the kinetic energy, the initial kinetic energy you solved here, right? We'll call this initial kinetic energy. And the final kinetic energy is the sum of the kinetic energies of the two fragments. So we have 1/2 times zero point 0.1, and they said it's going 1 meter per second, right? And then the other half is going, it's 1/2 times the mass, which is 0.06, times its velocity squared, which you get from here, right? So what is, if kinetic energy is conserved, if conserved, then kf equals k initial. This sum here will equal this up here. If they're equal, kinetic energy is conserved. If they're not equal, it's not conserved. So you should be able to answer that. So those are all my hints for this problem set.